The James Webb Space Telescope has revealed something astonishing on Triton, Neptune's largest moon, something NASA has yet to explain. Beneath its icy surface, a mysterious glow has been detected, unlike anything seen before, even with the most advanced telescopes. Could this strange light indicate hidden oceans, or perhaps something far more extraordinary? What secrets are being kept, and why? Join us as we delve into the mysteries of Triton and uncover what the government might not want us to know. This frozen moon holds a world of intrigue. Triton is unlike any other moon. It orbits Neptune in the opposite direction of the planet's rotation, hinting that it may have been captured from the Kuiper belt. The surface of Triton reflects much of the sunlight that hits it, giving it a bright, icy look. But beneath this reflective layer lies a world of possibilities, ancient impacts, cryovolcanic eruptions, and potentially even a hidden ocean. Thanks to the telescope's ability to detect infrared light, scientists can now map the moon's surface with incredible precision. Every molecule, every heat signature, and every change in its thin atmosphere provides a glimpse into its mysterious history and active present. What's hidden beneath Triton's surface is far more extraordinary than we could have imagined, and this is just the beginning of the discoveries that will continue to amaze us. One of the telescope's key strengths is its ability to analyze Triton's infrared spectrum. This technique is similar to a detective analyzing fingerprints, but these fingerprints belong to molecules. By studying the light reflected off Triton, scientists can detect methane, nitrogen, and other compounds frozen on its surface. These icy substances may hold clues about past geological events, like cryovolcanic activity, where cold, slushy materials erupted from beneath the moon's surface. Such discoveries would indicate that Triton is not just a frozen wasteland, but a geologically active world. The moon's atmosphere is also of great interest. Primarily composed of nitrogen, it is incredibly thin and dynamic. When sunlight hits the surface, some of the ice sublimates, transitioning directly from solid to gas and rising into the atmosphere. This process creates a delicate veil of activity that can be observed by telescopes. Monitoring gases like methane or carbon monoxide could offer clues about subsurface activities, possibly suggesting the presence of warm liquid reservoirs beneath the ice. The potential for a hidden ocean beneath Triton's icy surface is one of the most exciting possibilities. Tidal forces from Neptune's gravity might generate enough internal heat to keep a subsurface ocean in liquid form. This ocean may hold the fundamental components for life. While the telescope can't directly observe beneath Triton's surface, it can detect heat anomalies or unusual surface features that hint at liquid water below. For instance, a warm spot on the ice could signal active plumes releasing heat and material from beneath. What implications might this hidden ocean have for life? If it exists, it could interact with Triton's rocky core, forming a chemically rich environment similar to hydrothermal vents on Earth's ocean floor, which support thriving life despite the absence of sunlight. Triton's potential ocean might offer a similar refuge for microbial organisms. The discovery of such a habitat would have profound implications for our understanding of life beyond Earth. The telescope's findings on Triton could also reshape our understanding of the solar system. Triton's unique characteristics offer clues about the Kuiper belt, a distant region of icy bodies beyond Neptune. Understanding Triton's history might help scientists unravel how similar objects like Pluto formed and evolved. The moon's composition, geological activity, and potential subsurface ocean could serve as a template for studying other icy worlds in the solar system. Despite its advanced capabilities, the telescope encounters challenges when studying Triton. At a distance of around 2.8 billion miles from Earth, even the most sophisticated instruments struggle to capture detailed images. Moreover, Triton's faint reflected light demands extended observation periods, restricting the telescope's ability to monitor fast changes. Nonetheless, the telescope's findings are paving the way for future missions, such as orbiters or landers designed specifically to explore Triton's surface, atmosphere, and interior. With clues suggesting the presence of Triton's hidden layers, the prospect of a mission there is becoming increasingly exciting. Imagine a future mission sending a lander to Triton equipped with advanced tools. It could sample the surface ice, analyze its composition, and search for signs of past or present water. If plumes are detected, the lander might even collect material ejected from the moon's interior, providing direct evidence of its subsurface environment. Meanwhile, an orbiter could map the moon in high resolution, study its atmosphere in detail, and detect geological activity. Together, these missions would paint a comprehensive picture of Triton, transforming it from a distant curiosity into a well-understood world. The instruments on the telescope are ideally equipped for studying Triton. The near-infrared camera, NIRCam, detects wavelengths that penetrate through Triton's haze, capturing faint light reflected from its surface. By analyzing this light, scientists can pinpoint specific molecules and create an intricate map of the moon's composition. The near-infrared spectrograph, NIRSpec, disperses light into its individual wavelengths, revealing distinctive molecular signatures. This enables researchers to assess the distribution and temperature of materials across Triton's surface. Meanwhile, the mid-infrared instrument, MIR, enhances these capabilities by working with longer wavelengths. It can probe Triton's atmosphere and detect trace gases that might indicate ongoing geological processes. MIRI's ability to detect faint thermal radiation also provides insights into the moon's temperature and potential internal heat sources. These instruments together form a powerful toolkit for unraveling Triton's many layers. Exploring Triton is not without its challenges. The moon's distance from Earth makes any mission a formidable undertaking. Current propulsion technologies would require over a decade to reach Neptune's orbit. Additionally, the faint sunlight at this distance limits the use of solar power, necessitating alternative energy sources like nuclear power. The scientific benefits of studying Triton may outweigh the logistical challenges. However, it is also essential to balance exploration with planetary protection. If Triton contains life, even in its most basic forms, the introduction of Earth-based microbes could jeopardize its untouched environment. Future missions must be meticulous in sterilizing equipment and avoiding disruption of any potential ecosystems. This ethical responsibility highlights the need for careful and thoughtful exploration. While Triton's story is still unfolding, telescopes have already revealed a new chapter in our understanding of this enigmatic moon. Its observations could reveal whether Triton's surface bears the scars of ancient impacts, cryovolcanic eruptions, or other dynamic processes. The data might also confirm the presence of a hidden ocean, a discovery that would reshape our view of habitable environments in the solar system. By studying Triton, scientists hope to answer broader questions about the origins and evolution of icy worlds. Was Triton always part of Neptune's system, or was it captured from the Kuiper Belt? How do its geological and atmospheric processes compare to other moons like Europa and Enceladus? These questions extend beyond Triton, offering insights into the broader mechanisms that shape our cosmic neighborhood. Triton's potential to support life raises profound questions about the existence of life elsewhere in the universe. If an ocean lies beneath its icy surface and contains the necessary chemical ingredients, could life have emerged there? Finding even microbial life on Triton would be one of the greatest scientific milestones, showing that Earth is not the only planet capable of hosting life. The journey to understand Triton is only just beginning. While telescope observations are laying the groundwork for future exploration, there is still much to uncover. Whether through advanced telescopes, robotic missions, or even human expeditions, Triton offers the exciting possibility of revealing new insights about our solar system and the potential for life beyond Earth. Though it is a cold and distant moon, its potential for warmth and activity makes it a beacon for scientific discovery. Step by step, human efforts have reached deeper into space, building the knowledge and tools needed to uncover the wonders of distant places like Triton. From rockets to space stations, space exploration is one of those things that humans just couldn't stop chasing ever since they looked up and wondered what those twinkling dots in the sky were. From basic stargazing to building telescopes that could zoom in on other planets, we've come a long way. Back in the days before electricity or modern science, people would track the stars and planets with tools no more complex than sticks and stones. These ancient observations laid the groundwork for what would eventually spark our quest to reach the stars. Fast forward to the early 17th century, and things took a more serious turn with the invention of the telescope. Suddenly, the universe felt much closer. Galileo directed his telescope toward Jupiter and observed its moons orbiting around it. He also saw Venus's phases, providing evidence that not everything revolved around Earth. A groundbreaking realization at the time. This marked the beginning of humanity's understanding that the cosmos was far more intricate than previously imagined. By the early 20th century, space travel had evolved from a mere science fiction concept into a tangible goal. A handful of scientists, like Konstantin Tsiolkovsky in Russia and Robert Goddard in the United States, started figuring out how rockets could actually work. Tsiolkovsky imagined rockets using liquid fuel instead of gunpowder, and Goddard made it happen. In 1926, Goddard launched the first liquid-fueled rocket, a small but groundbreaking step toward getting humans off this planet. The mid-20th century brought the space race, a heated rivalry between the United States and the Soviet Union. In 1957, the Soviets launched Sputnik 1, a shiny metal ball that became the first artificial satellite to orbit Earth. This event stunned the world and gave the Soviets a significant lead in space exploration. Feeling the pressure, the United States swiftly founded NASA in 1958, igniting a fierce race to dominate space. The 1960s saw rapid advancements, starting with Yuri Gagarin's groundbreaking 1961 mission as the first human to orbit Earth aboard Vostok 1. Shortly after, Alan Shepard became the first American in space, although his flight was a brief suborbital journey. Inspired by these milestones, President John F. Kennedy set an ambitious goal: land an American on the moon and return them safely before the decade ended. This mission wasn't just about exploration, it was a bid to establish global supremacy. NASA's Apollo program took on this challenge with determination. After several test missions, Apollo 11 touched down on the moon in July 1969. Neil Armstrong and Buzz Aldrin became the first humans to walk on another world, leaving footprints that would become symbols of human achievement. Michael Collins, the third astronaut, stayed in orbit around the moon, waiting for their safe return. Armstrong's words, "That's one small step for man, one giant leap for mankind," captured the significance of the moment. The moon missions didn't stop there. Between 1969 and 1972, NASA sent 5 more crews to the lunar surface, collecting rocks and conducting experiments that revealed new insights about the moon's history. Apollo 17, the final mission of the Apollo program, concluded this remarkable era, leaving behind a lasting legacy of ambition and innovation. In the 1970s, space exploration took a new direction, focusing on extended stays in space. The Soviet Union launched a series of space stations known as Salyut, starting with Salyut 1 in 1971, demonstrating that humans could live and work in space for weeks, even months. Meanwhile, NASA in the United States launched Skylab in 1973, conducting groundbreaking experiments in microgravity and studying the sun in unprecedented detail. The 1980s introduced a new era with the advent of reusable spacecraft. NASA's Space Shuttle program took off with the launch of Columbia in 1981. The shuttle wasn't just about getting to space, it was about making space travel more routine. These vehicles deployed satellites, repaired equipment, and played a key role in building the International Space Station, ISS. But the program wasn't without its tragedies. The Challenger explosion in 1986 and the Columbia disaster in 2003 served as harsh reminders of the risks involved. Despite these setbacks, international collaboration became a defining feature of space exploration. The International Space Station, ISS, orbiting Earth since 2000, is a collaboration between NASA, Russia's Roscosmos, and space agencies from Europe, Japan, and Canada. It serves as more than just a space station. It's a floating laboratory where scientists conduct unique experiments that can't be carried out anywhere else. The ISS also stands as a testament to what can be achieved when nations come together, even amidst political challenges. At the same time, robots have played their part in exploration, reaching places that humans have yet to access. NASA's Voyager probes, launched in 1977, journeyed to the outer planets and beyond. These spacecraft are now sending back data from interstellar space, giving us a glimpse of what lies outside our solar system. Mars has been another major focus, with rovers like Spirit, Opportunity, Curiosity, and Perseverance crawling across its surface to search for signs of life in the 21st century. Private companies entered the space game, bringing new energy and innovation. SpaceX, founded by Elon Musk, became a leader in commercial spaceflight. In 2008, its Falcon 1 rocket became the first privately developed rocket to reach orbit. SpaceX followed this with the Falcon 9 and the Dragon spacecraft, which now transport supplies and astronauts to the ISS. In 2020, the Crew Dragon mission made history as the first commercial spacecraft to transport humans into orbit. Companies like Blue Origin and Virgin Galactic are also gaining attention, with a focus on suborbital flights and space tourism. This shift toward privatization is transforming space exploration, moving it away from government-led programs and toward commercial ventures. With billionaires backing these initiatives, the future of space travel is becoming more accessible, at least for those who can afford the steep costs. Looking ahead, the focus is turning back to the moon and further into space. NASA's Artemis program aims to land astronauts on the moon again, this time to establish a long-term presence. The program promises to send the first woman and the next man to the lunar surface, paving the way for eventual missions to Mars. This isn't just about exploration. It's about building the technology and skills needed to survive on other planets. International collaboration remains crucial, with Europe, China, and other countries contributing to ambitious projects. China, for example, has been making impressive strides with its space program, from crewed missions to the Tiangong space station to lunar exploration with the Chang'e missions. These efforts demonstrate that space exploration is no longer controlled by just a few entities. It has become a global pursuit. From dark matter to far-off galaxies, each new discovery brings us a step closer to unraveling the mysteries of the universe and understanding the unseen forces that shape the cosmos. The universe is vast and perplexing, filled with far more questions than answers. One of the greatest mysteries is dark matter, a mysterious substance that neither emits, absorbs, nor reflects light. It's like an invisible force binding galaxies, yet we can only speculate about its true nature. Scientists have suggested particles like WIMPs or axions might be the culprits, but nobody has nailed it down. Figuring out dark matter is vital because it shapes how galaxies form and move across the cosmos. Then there's dark energy, which is even weirder. It's believed to make up over 2/3 of everything in the universe and is pushing galaxies farther apart. Imagine a force so powerful that it's expanding space itself. Some say it's just a property of space, while others think it could be something entirely new. Whatever it is, dark energy holds the key to understanding whether the universe will keep growing forever or collapse back in on itself. The origin of the universe is another perplexing mystery. The Big Bang Theory describes how the universe began as a hot, dense point, but what triggered the Big Bang? Was there anything before it? Some theories, such as cosmic inflation, propose that the universe expanded faster than the speed of light right after its creation, smoothing out everything we observe today. However, the exact causes and reasoning behind this remain unresolved. Black holes, often seen as the universe's ultimate vacuum cleaners, pull in everything, even light. While we know they exist, the questions they present are truly staggering. For example, what happens to information that falls into a black hole? This information paradox has physicists scratching their heads because it clashes with how quantum mechanics says the universe should work. Solving this could bring us closer to a unified theory of everything. Galaxies come in all shapes and sizes, but how did they get that way? Observations show massive variations, and some galaxies from the early universe seem way more developed than they should be. It's not just dark matter, but also the influence of black holes at their centers that shape these cosmic structures. Grasping this could revolutionize our understanding of galaxy formation. And don't even get started on the immense voids between galaxy clusters. These vast emptinesses might hold the key to understanding how dark energy operates on a cosmic scale. The search for life beyond Earth is one of the most thrilling areas of exploration. Thousands of exoplanets have been discovered, with some possibly capable of supporting life. But detecting biosignatures like specific gases in an atmosphere is no easy task. New technologies such as the James Webb Space Telescope are working toward this goal, but for now, it's a waiting game. What if life exists on a distant planet, just waiting to be uncovered? Meanwhile, neutrinos, tiny particles zipping through the universe, are another problem. They barely interact with matter, but they're everywhere. Scientists are still trying to measure their exact properties and figure out what role they play in the grand cosmic design. The more we learn about them, the more they might reshape our understanding of physics.